A stellar flare called RS Serpentor has erupted 4,500 light-years away in the constellation Serpent. This flame was so bright that it can now be seen with the naked eye. Its magnitude is about 4.8, a full 7 magnitudes brighter than normal. New stars are rare, but RS Serpens is an even more interesting case. This is because the cataclysmic variable star that flares up from time to time in front of us, and there are only 10 such stars in the Milky Way. Snake's RS has a flame periodicity of about 15 years, a white quartet in close orbit with a red giant. As they orbit each other, gas, primarily hydrogen, is ejected from the red giant by the white dwarf, which is smaller and denser. This hydrogen then collects on the surface of the white dwarf, where it is heated. Occasionally, its mass becomes so great that the pressure and temperature below cause a thermometric explosion, ejecting excess matter into space at a speed of 2,600 kilometers per second. If the white dwarf accumulates so much mass that it exceeds a critical threshold, it will become unstable and explode in a supernova. This snake may also happen with MS, but for now the two stars continue to live in close orbits. After a quick flash over the next few weeks, serpentine MS will gradually fade and eventually disappear. The next discovery will be only in 15 years, so astronomers advise not to delay the observations. The constellation Serpent is visible to the south. It is not very bright, so it is recommended to look for a new one in the backlight, not in the city. Remember and have a good hunt. The Milky Way galaxy is a medium-sized galaxy. This galactic island may have as many as 100 billion planets. It should be noted that most of them have not yet been studied. Exploring our galaxy will probably take hundreds, if not thousands, of years from our apartment closet. And yet, each of the exoplanets confirmed by astronomers has unique features and characteristics, sometimes radically different from what you and I see. This uniqueness can manifest itself in many ways. Today we're going to tell you about two interesting exoplanets that not only orbit their closest parent star, but eventually become something more. In our solar system, the closest planet to our star is Mercury, the smallest of the terrestrial planets. It moves at a speed of 47 kilometers per second at a distance of 58 million kilometers from the Sun. However, it is far from the record holder in terms of speed and proximity to the parent star. The name now boasts a very large Jupiter-class planet. TOI 2109b orbits a star in a star system located 855 light-years away, with a record low orbital period. It takes only 16 hours to complete its orbit. Come to think of it, you're not out of date yet. And it's New Year's Eve on planet TOI 2109b, and even though the Christmas tree is lit, there doesn't seem to be anyone there to celebrate. Because the daytime temperature is about 3,225 degrees, which is almost the temperature of small stars, so there is no such thing as light tan. TOI 2109b is about 2. At 4 million miles from its star, the gas giant is in tidal lock, and because of its close proximity to the planet star, the TOI 2109 system is an ideal laboratory. Study of planetary wave breaking by the gravitational pull of stars. Planets close to their stars that are still on the main sequence in the Hertzsprung-Russell scheme, that is, have thermometric reactions of hydrogen to helium fusion in their cores. What does this mean? Consider the following example. According to modern representatives, white swans may have companion planets. Until recently, a direct indication of this was not known. But recently, in the constellation Dragon, 80 light-years away from us, an unusual white dwarf whose companion is regularly eclipsed was discovered. It blocks most of the light that reaches the bush from the ground. According to the researchers, This companion could be a planet of the type and size of Jupiter, or, less likely, a brown dwarf. These observations were also supported by data from the Spitzer Space Infrared Telescope. The collected data allowed us to determine with complete confidence that WD 1856-534, a transiting white dwarf companion of Jupiter. On its own, this doll is nothing special. With a temperature of 4,500 degrees Celsius, it is cooler than the Sun. This means that it formed about 6 billion years ago, long before the formation of the solar system, and has had some time to cool down since then. It has about half the mass of the Sun, and its radius is 75 times smaller than that of the Sun, or 40% larger than that of Earth. Of course, it is not simple in the sense that it is an external component of the visual three-star system. Internal components. The white dwarf companion, designated WD1856b, has a large semi-major ellipse with a length of 0.02 solar units. In other words, it is 3 million miles from its star, which is 20 times smaller than the average orbital radius of Mercury mentioned above. The radius of this body is more than 10 times that of Earth. Thus, compared to the star WD 1856-534, the object looks like a true giant. This explains the strong conservation of dwarf light that the researchers found. WD 1856b is known to have an orbital period of only 34 hours around the white quaternary. Unfortunately, the exact mass of the satellite planet is still unknown. To determine its radius, we need to know its radial velocity, which has not yet been determined. This velocity is measured by the Doppler shift of the spectral lines, which are not visible in this case. Nevertheless, we still learn something interesting when we compare the results of light conservation observations made with the giant telescope photometers on the island of La Palma with similar observations in the near-infrared region, with equipment, Spitzer telescope. Thus, the dynamics of light changes in both ranges turned out to be almost the same. After that, the exoplanet's thermal radiation flux is no more than 6% of the dwarf flux. That is, such a dark body could be a giant planet, or a very low-mass brown dwarf. Recent analysis suggests that the mass of WD 1856b should not exceed 13.8 Jupiter masses. This estimate is almost equal to, but slightly below, the theoretical low associated with the mass of brown bushes, so selection in their favor is unlikely. Based on the available information, we can confirm that we are talking about an incredibly large planet. But as a companion, WD 1856b could be 3 million miles away from the white dwarf. And how it may have escaped the star's death. The fact is that in the process of becoming a red giant, the star absorbs its planets very closely. The Sun will destroy Mercury, Venus, and possibly Earth in about 5 billion years. But how did planet WD 1856b survive? Because in its current orbit, it would have burned up long ago. The researchers suggest two plausible scenarios to consider. First, White Darvish's star was originally supposed to be a red giant before it died, blossoming with an ego the size of Earth's orbit. If a planet is at short distance, it would have been completely enveloped by the giant's outer shell, and if it had been surrounded by hot gas, it would have lost its burnt-out outer layers, but may have retained its inner chambers. Moving in a cloud of gas plasma, it was braked by friction and approached the dense core of the star, after which it threw off gas shells and became a white bush. After jettisoning, the planet was once again in gas-free space, and it entered a stable orbit around the dwarf. If the shedding of the red giant's crust is delayed, the planet will continue to accelerate and eventually collide with the star's core in a catastrophic cataclysm. Astronomers on Earth would not have expected the white owl and its companion to survive. Whether the satellite itself, a planet, or a brown dwarf, was to be completely destroyed. However, this scenario is less likely as model simulations show that it is impossible for the outer shell of the red giant to completely stabilize the satellite's orbit due to the operation of several dynamical mechanisms. Here we come to the second scenario. The same simulations show that the progeny star had multiple planets in distant orbits, and after becoming a red giant, their orbits lost their previous stability. As a result, the planet WD-1856b gradually moved into a trajectory near the dwarf, and the others, if any, were thrown into free flight through space. This restructuring can take about 1 billion years, which corresponds to the age of the white dwarf. It's like what happened, and once the planet was bigger than the star, it orbited. Yes, space is definitely an interesting place, full of interesting and even mysterious phenomena and objects. Well, for a custom James Webb telescope, there's a lot of work ahead, including learning about this amazing couple. I hope that still solves the question about the nature of the WD-1856b output. A mysterious object. However, some supernova explosions are probably not powerful enough to completely destroy nearby stars, like what happened with the LP-4365 White 4. An international team of astronomers has received new information about a mysterious object seen in 2017 dubbed the Runaway star from the hotspots. This space shuttle appears to have traveled the entire Milky Way at a speed of about 3.5 million kilometers per hour. And it's moving in the wrong direction, where most of the stars are in the center of our galaxy. Another anomaly was discovered. This object is made of a completely different material than the rest of the stars in the Milky Way. It is filled with heavy metal atoms, while other stars are dominated by light chemical elements. The incredible speed of movement suggests that the object is trying to leave the boundaries of our galaxy. Based on this fact, astronomers have proposed in a new study that such a speed could develop a celestial body that survived a violent cosmic catastrophe. It has been suspected that a supernova explosion resulting in a powerful release of energy could give the star a massive boost. This is quite possible if the object is part of a binary star system consisting of a pair of white dwarfs. The fate of such small but powerful stars is typical. Over time, one star drains so much mass and energy from its vampire-like partner that it eventually explodes. Such explosions are so powerful that they fuse the cores of old elements into completely new elements, then shoot the star in any direction. Now a new traveler with no orbit and no satellites is speeding toward the edge of our galaxy. What happens after that? Will he be able to leave the galaxy or return? We no longer recognize it. Chemical elements are the basic identifying forms of the material world. The periodic table of chemical elements is considered one of the greatest achievements of chemistry. Today, it is considered almost twice as much as it was half a year ago, when it published Dmitry Ivanovich Mendeleev's experiments on the system of elements based on atomic weights and chemical combinations. As it turns out, this sheet is the reason why our world appeared not only on Earth, but also outside. For example, the chemical composition of the Sun's surface is mostly 74% hydrogen and 24% helium. Their predominance characterizes our stellar nature. Iron, sulfur, magnesium, calcium, oxygen, etc. Elements such as are present in small amounts. Yes, almost all stars are made of gas. If the stars make sense, there is something more mysterious in the universe. For example, black holes. Of course, like the Sun, or a neutron star, most of Mendeleev's table could contain a black hole. But in what form? Black holes are a fantastic phenomenon in space. We don't know much about them. And this raises the question of whether there are elements inherent in cosmic bodies and effects in our universe that humanity does not know about. Today, we will try to understand it in short and convenient language. Physicist Richard Feynman is said to have invoked the theory of relativity to predict the end of the periodic table at element 137. His calculations showed that electrons in elements above 137 must travel faster than the speed of light, and thus violate the laws of relativity. True, recent calculations have eliminated this limit. Feynman viewed the nucleus as a single point. Let it be a ball of particles, and the elements can live up to about 173. There may be atoms beyond this limit, but only strange entities that can summon electrons from space. Relativity is not the only problem. Positively charged protons repel each other, so the more of them in the nucleus, the more stable it is. Uranium, with atomic number 92, is the last naturally occurring stable element on Earth. Each element then has a rapidly decaying nucleus, and their half-life is time. The time required for half of a material to decay can be minutes, seconds, or even fractions of a second. Atomic physics in the early 1930s seems to be a strange pattern. Nuclei in which the number of protons and neutrons is 2, 8, 20, 28, 50, 82, or 126, and were characterized by high stability or stability. This regularity was confirmed not only by physical experiments, but also by analyzing the distribution of various elements in nature. By distribution, you can judge how stable an element is. Natural reserves of elements such as tin, which has 50 protons in its nucleus, barium with 82 neutrons, and steel, which has 82 protons in its nucleus, are much larger than those of their neighbors in the periodic table. At that time, these facts did not find any explanation, and physicists began to jokingly call such a number of protons and neutrons magic. It is fortunate that this discovery was not made during the Inquisition. Then it was also noted that if both the number of protons and the number of neutrons are equal to magic numbers, the nucleus is characterized by a particularly high stability. An example of such a binary nucleus is the isotope iron 208, which has 126 neutrons and 82 protons. Current theory has succeeded in explaining the pattern of formation of magic numbers. Like the electrons of an atom, the neutron and proton shells in the nucleus are formed. The structure of atomic shells is quite different from that of electron shells, but the most stable nuclei are isotopes with neutron and proton shells filled. Thus, a superelement with a twice-magic nucleus is predicted to be element 126. A doubly magical isotope of this element must have 184 neutrons in its nucleus. This magic number is theoretically calculated to be in the region of atomic number 126, so we will be seeing isotopes for a lifetime to study their properties. But how long such isotopes will live, days, months, years, is still unpredictable. Another region of stable isotopes is expected around atomic number 114. Researchers face great difficulty in determining the properties of distant elements such as 114 or 126. Furthermore, there is no absolute certainty that there should be areas of stability. The most interesting search. If regions of stability are not found, current ideas about nuclear structure will have to be revised. If the prediction of the existence of new regions of stability of the elements is justified, it will open new perspectives for investigating the properties of transuranic elements, as well as confirm the existence of the idea and make a great contribution to nuclear physics. Structure OF is the nucleus. Of course, heavier and more unstable elements may exist elsewhere in the universe, such as dense neutron stars. But for obvious reasons, it will be difficult to study them directly, because you can quickly get into a breakdown to the table. But the good thing about modern laboratories is that they can achieve amazing results that unlock these chemical mysteries. Typically, new elements are created as follows. For example, we have a lighter atom called calcium. It accelerated and crashed into a foil of heavier atoms. If an accelerated atom moves fast enough, its nucleus, the compact nucleus of a proton, and neutrons in its center, can come into contact with the nucleus of one of the heavier atoms. If this is the case, they will combine to form a heavier element. Although a sheet of foil appears solid to the human eye, it is very different at the atomic scale. The nucleus occupies only a small fraction of the space occupied by the atom as a whole. And to create a new element, the nuclei of each atom must collide and combine. It's incredibly difficult. Here's why. If you imagine an atom about 170 meters in size, the center is a tiny grape. But there is another complication. If two nuclei are headed for a collision, they must overcome a strong repulsive force that prevents them from fusing into a new element. It is called electrostatic, or Coulomb force. Only if the nuclei collide with enough energy will they overcome this force and eventually fuse together to form a new element. Let's call him Rudius. The theory so far predicts that new nuclei created in the lab will not survive long enough to form a real atom. Because less than 10 trillionth of a second, a radioactive nucleus would not have time to collect electrons around it and create a new element. But things may work differently in space. The fact is that with great gravity, constant or variable temperature, new elements of matter not only abundantly replenish the table, but can also go to a new level unknown to us. Yes, it is possible that black holes consist of a complete set, or nearly complete set, of primordial particles that decay into energy, perhaps into an indescribably fantastic conglomeration. For example, neutron stars, the precursors to black holes, are thought to have an upper mass limit of 3 solar masses. It is the maximum density of matter that is equal to the nucleus when all neutrons have all their quantum states. And these energies and forces of modern physics are known. And here the combination of these energies can create something unknown to science. What would happen if a supernova exploded near Earth? Actually, there are 3 answers, none of which are very comforting. But before we answer them, let's try to understand what a supernova birth is, and why they can harm all life, even if they are very distant. Thus, a supernova, or supernova explosion, occurs when a star rapidly increases in brightness and then collapses relatively slowly. A supernova is observed post facto, that is, after the event and its radiation reaches our keen eyes. A supernova occurs when there is a change in the center or core of a star. The change can take 2 forms, and both lead to a supernova. The first type of supernova occurs in a binary star system. A binary star is 2 stars orbiting the same point. One of the stars, White 4, steals matter from its companion star. Eventually, the white dwarf accumulates an inappropriate amount of matter, and too much matter causes the star to explode. This is how a supernova is formed. The second type of supernova occurs at the end of a star's life. When a star runs out of nuclear fuel, part of its mass falls to the core. Eventually, the core becomes so heavy that it cannot resist its own gravity. The core collapses, causing a supernova star to explode. A powerful supernova explosion is the final stage of evolution, resulting in the formation of a new astronomical body, a neutron star, or a black hole in the universe. What kind of object a supernova transforms into depends on how the next stage of evolution proceeds. If the gravitational collapse is stopped by the internal pressure, a neutron star forms. Such stars are compact, with a radius of no more than 10 kilometers. a high density of up to 1 billion tons per cubic centimeter and 2.5 times the mass of the Sun. After a supernova explosion, two types of neutron stars remain: pulsars and magnetars. The former is 10 times heavier than the Sun, and the latter is 40 times heavier. Pulsars spin at high speeds on their axis, creating an energy field, and the poles emit pulses of radiation. The strength of the magnetar's magnetic field is 50 trillion times stronger than that surrounding the Earth. If the mass of the supernova exceeds the mass of the Sun by a factor of 40, there is a 100% chance that the supernova formed after the star exploded. Black holes form as a result of gravitational collapse. When a supernova has a mass of 100 times the mass of the Sun or more, this result is highly probable. Black holes attract an incredibly large amount of particles every second, quantities comparable to millions of Earth masses. Excess energy is emitted back into space as radiation. Such is the future of our nearest stars. Yes, it's Betelgeuse, which is 20 times more massive than our Sun. It is now in the red giant stage, albeit a long-term dead stage. Betelgeuse is one of the brightest stars in the sky. The red dot in the constellation Orion continues to amaze with its mysterious behavior. At the end of 2020, it faded, but now it is back and has become 50% brighter in a few weeks. This is what led to rumors that Betelgeuse would explode. It's not hundreds of years, it's decades or even years. Eventually, when the star runs out of fuel, it will collapse due to gravity and go supernova. What if Betelgeuse explodes now? Should we pack our bags and gear and grab a bloody guinea pig for the bunker? Yes, sometimes people start doing things when it's too late and after the last star has left the station. And it is better to prepare everything in advance. So if it's Betelgeuse, we shouldn't expect much danger. Yes, the spectacle would be spectacular, but the Earth would not be shaken by the shock wave. The towers of heaven would not fall like staves. The sea would not rise like walls, and the inhabitants would not be kindled by fire. The last day of the apocalypse. I'm sorry, Thanos. So what do we see? According to calculations, it should be the second supernova explosion. This means that Betelgeuse, to an observer in its own system, will briefly be 500 million times brighter than our Sun. Yes, indeed, it is blindingly bright. But of course, we don't roll Betelgeuse. How bright will Betelgeuse be for us? Given the distance from Earth to the giant, calculations show that Betelgeuse will be about half as bright as the Moon. Betelgeuse will be visible both during the day and at night. But it will not be like the second Sun. During the day, Betelgeuse will appear as a large, bright spot, larger than an ordinary star, but smaller than the Sun. At night, Betelgeuse will appear as a large, bright cloud, comparable in brightness to the Moon. Over the coming months, Betelgeuse will begin to fade, but will remain visible during the day for 6 months, or up to a year. For another 2 years, it can be observed with the naked eye in the night sky. Only then will it disappear. Unfortunately, not a single dome is visible around an exploding supernova at a time. That's a long time, so we'll have to wait a few more years before we see a spectacular dome around a once-dead star. Astronomers with their powerful telescopes will soon be able to see the star's crust. Fact: the big boss in Betelgeuse is 642 light-years from Earth, so its supernova maximum will shower our planet with massless particles called neutrinos. Fortunately, they cannot harm us.